Now the next thing we'll move on to is inverse functions. So an inverse function, so say inverse of f of x undoes what f of x has done. So turns y back into x essentially. And the notation is that it's poor notation because it could be interpreted as like to the power of -1, but that's just the notation. Deal with it. And so if we, just a few things before we get into like some of the things you really need to know, just some basics about it. So if we had x to y, and then this is how we go our f of x, we call this our domain, and this our range, right? And then when we go put f inverse of x here, suddenly, because this is a function, this becomes the domain, and this becomes a range. So this is how we can say that the domain of f inverse of x is equal to the range of f of x. And then likewise the range of f inverse of x is simply the domain of f of x. And that can be very helpful in solving problems. But then not every function has an inverse function. This is important. If you recall, we had several examples of stuff. We had several examples, and this is like x minus 2. Of relations on a graph. And we talked about which ones were functions and not. And we determined that these were functions because they passed the horizontal line test. And if you would have to answer that in an exam, you'd say it is a function because it only has one output for every input. And then these weren't functions. But additionally, if we think about inversing them, so 2x minus 1, say we put in 2 times 5 minus 1, which is equal to 9. To get back to 5, we'd have to do x plus 1 over 2. And let's just bear with me here. And then so that would become a much less steep curve, and it would be like a bit more like that. And notice how this is still a function because it still passes the vertical line test. But say if we did this one here, which is x minus 2 squared minus 2, we did y plus 2, and then the square root, and add 2, and remember this has to be plus or minus, so we'll get something like that. And that does not pass our vertical line test. Therefore, its inverse is not a function, so it doesn't have an inverse function. And the difference between these is this is 1, 1, and this is many to 1. And so that's why we can say only 1-to-1 functions have an inverse. And I did a few things where I worked out the inverse functions, and if that's looking a bit confusing to you, I will now explain it. So essentially, what the simple way, if I do a linear one again, and this, what I'd say is I'd replace this with y, that f of x with y. Then what I'd do is I'd change x and y, and then I'd make y the subject. And then I'd have to finish off by saying, using the correct notation. We started with f of x, we must end with f inverse of x. And that's essentially how you work out an inverse function. That's the easiest way to do it. You swap x and y, and then you make y the subject. And it comes from the fact that, it's just essentially reverse BEDMAS. So we've done this, okay, 5, we multiply it by 5, then we subtract 8 to get the answer. So if we want to reverse that, we'll do all our addition subtraction first in reverse. So, okay, we'll add 8, and then to get rid of that 5, we'll divide by 5. And that's exactly what we do here. But this is a way, for non-linear functions, this is a good way to make it quicker. And for this one, then, change them around, plus or minus, that should be an x, and then y equals 2 plus or minus x plus 2. And this not a function because it fails the vertical line test, and it does not have only one input for every input. And so also if it asks you why does a function not have an inverse, you'd say it's not 1-to-1. That's easy mark. And additionally, notice that for this inverse, if I drew it a bit better, so we're doing 2x minus 1, say this is minus 2, and that's positive 2. It'd look something like this. And then what did we decide it was? Yes, x plus 1 over 2, so that's like that. Half x and going up a half. Actually, 2x minus 1, it must start at minus 1 like that, sorry. And then, that was the eraser. I was wondering why this wasn't working. And then our inverse one will look roughly like this. And notice that if we drew the line y equals x, these two are reflections in it. They're mirror images in the line y equals x. And that is the relationship between those inverse functions. And this one is dreadful. Sorry, it should be more like this. It crosses the one like that. This is a terrible sketch because it's difficult. But yeah, that's a relationship between the mirror line, a function and its inverse. They are reflections of each other in the line y equals x. And additionally, you may we talk about, if I move on to another page, we talk about many-to-one functions not having an inverse. But there are ways that we can make this one-to-one. We can restrict the domain. Imagine this is x squared minus 2. And suddenly we just said for x is greater than 2. And that would mean is, well, x 2 squared is 4 minus 2. So we're roughly along here. And what that looks like on a graph is this. We've gotten rid of everything over there. So now, this is actually now is 1-to-1. So this would have an inverse. And so we could say that x squared minus 2 equals y, y squared minus 2 equals x, y squared equals x plus 2, y equals x plus 2 square root. And because we did greater than a number, it's the positive root. And then it would look a bit like that. And we have y equals x as the mirror line. And we could have done smaller than 2 and still be 1, 1. But at this point, at x equals 0, because of that nature, which is because it's the vertex, because x, well, that's x minus 0 squared minus 2, because there's no x to the power of 1 involved. That vertex is at 0 minus 2. So you could have gone to 0, but as soon as you go past that, no longer 1, 1. So it can do things like, say, for which value, you could say something like x squared minus 4, for x is greater or equal to k, find smallest k that this is 1, 1. And what you do is you would, if it was more complicated than that, you'd complete the square. And this one is very easy because there's no b-term. And essentially for and then for things like reciprocal functions, you gotta essentially think very carefully about what you do there. Well, actually, no, even reciprocal functions you'd be fine. It'd be something like involving things like several negative powers or something like that, and you just have to potentially make something 0. Generally, the approach would be to make something 0, and you get that because you have to essentially figure out where the maximum and the minimum points, where the graph kind of turns and comes, hits repeat values, and at that point cut it off. It may sound a lot more complicated than it really is, but trust me, you'll figure it out. And there is also a special case of function called self-inverse. And that's when the f of x equals f inverse of x. And that implies, well, does it? I mean, more than implies, says f of x is symmetrical in the line y equals x. On some final notes, note that the f inverse of x, well, sorry, I should say f inverse of the f of x is equal to is actually equal to f of the f inverse of x, which is just equal to x. And an important corollary I should note of the self-inverse is that f of x is equal to x as well, because this either of them can be interchanged with f inverse of x, so that should make sense. And what I meant earlier about things like with fractions and stuff is something like maybe like 2x squared. And then that's fairly simple. You just make this part 0, because then that would be where it honestly looks a bit like this, because this approaches infinity at a certain point when this bracket is equal to 0. And so 2x minus 3 equals 0, 2x equals 3, x equals 3 over 2. So this would be 3 over 2, and your answer would be 3 over 2 in that question. And just a reminder of a few things that I think you need to remember is just you remember these facts, because they will help with finding ranges and stuff. And this again also helpful. In fact, I may just do a quick example. Says f inverse of x equals 5x minus 1 over x for 0x 3. So this is the domain. And if we wanted the range of, the domain of that, we just need to calculate the range of f inverse of x. So we figure this out. We start here. 5 times 0 minus 1 over 0. Oh, can't exist. That's infinity. And then we try this one. 5 times 3 minus 1 over 3. That's 14 over 3. And we know that as you keep making that one smaller, it'll only get bigger and it'll approach infinity. So you'd say that the domain here, because that range is f inverse of x is greater or equal to 14 over 3, then the domain would be x is greater or equal to 14 over 3. Oops, hang on. No, because if you keep making that smaller, then 5 times 2 minus 1 over 2 is 9 over 2. That's getting smaller, sorry. That, I got the signs the wrong way around. That'll be smaller, and that'll be smaller. Sorry about that. But the point is the same. We're using the fact that the domain of f of x is equal to the range of f inverse of x, and the range of f of x would be the domain of f inverse of x.